Let's analyze this, right? So we said that there are at most n-1 operations, right? That part is clear. N-1 edges. So this loop will be executed n-1 times when I'm doing a merge. And how many finds am I doing? Inside this, I'm doing 2 find operations and at most 1 merge operation. Yeah. So therefore, what is the total number of operations? Total operations I'm doing is 2 times n-1 finds plus n-1 merge. Okay. And the crux is that this can be done in order n time using the algorithm of ranking and path compression. Okay, using this algorithm. Okay. So again, we are not going to get into this algorithm, right? All right. And this time would actually be order n log star n. Okay. Yeah, so the time it will take is order n log star n, but log star n is a function that is so small that even if you consider all the atoms in the universe, if n is equal to all the atoms in the universe, then log star n would be equal to 5. Okay, so pretty much, for all practical purposes, we take log star n to be a constant. Okay, so we'll just say that this is order n time. Yeah, so that's the algorithm. Now let's analyze it, right? What was the sequential time? We said it's theta n square for dense graphs. Yeah. So what about the parallel time? Every processor has to do the DFS, right? And that is proportional to the number of edges that are visible to it. And what is the number of edges visible to any processor? Theta n square by p. Yeah, is that clear? That's the way we did the row division of the matrix, right? Of the adjacency matrix. Okay, so that's your compute component. And then you have the merge component. So it takes order n time to do all the operations, right? The finds and merge. And then you have to do this log p times, right? Because there are p processors. So this is your total time to do merge. Okay. So now what's your speed up? Speed up is sequential time by parallel time. So that's going to be theta n square divided by theta n square by p plus theta n log p. I can simplify this if I just divide by n square, numerator and denominator both by n square, I'll get 1 upon theta 1 by p plus theta log p by n. Okay. And what is efficiency? Efficiency is going to be speed up divided by p. So you want your efficiency to be as close to 1 as possible, a constant, right? Preferably. If you divide by p, so the denominator gets multiplied by p. So you get 1 plus theta of p log p by n. So what is the maximum number of processes I can use in order to get a constant efficiency? If I take processes to be order of n divided by log n. So if I take processes to be order n by log n, then p log p by n will become n by log n into log p will be log of n by log n, which is pretty much log n, divided by n, right, which will be 1. Okay, so that's the idea, which is quite okay, right? N by log n is a very large number. For theoretical interest, yes, you would want to get some other algorithm where efficiency is 1, but for all practical purposes, p is much smaller than n. Okay, so this suffices. This was basically the discussion on parallelization of connected components and DFS, right? This is pretty much the algorithm for DFS as well. Well, not the forest per se. You will have to do more work if you want to maintain the forest as well, right? You'll have to drop some edges, you'll have to retain some edges. So can be done. That will be another algorithm. When you merge, right, what is the communication involved when you merge? On different processes, what do I actually need to do in order to do the merge? Any ideas? How can I do this? What will the communication be? So this information is residing on different processors, right? What do I send where in order to do this? The merging of the two forests, right? That involves find operations, merge operations, so on. I can't send the list of all the edges, right? That's an overkill. Well, there are different ways of doing it. One way is that I could do a find for all the vertices. So I could look at all the vertices at the endpoints here, send that list to B, and then it's just up to B, right? It just has to do a find on all of these. Well, I don't want to send all the edges. That's more than theta n work, right? That could be n square by P edges, right? I don't want to send that much information. I want to send theta n information. Is that doable? Can I send the list of vertices? Okay, interesting question. So I'm going to leave this as an exercise. Okay, so think about it. How am I going to do this communication? So one way of doing the communication, the simplest way is that I do each of these operations separately, right? When I want to do a find of 1 and 2, I send it to B, right? And B sends me back the sets that they belong to, right? And then I just simply figure out whether they are in the same component or not, and I just merge if necessary. But that's going to be theta n square by P. So can you think of something better? How can I do this in theta n with only theta n communication? Okay, so think about it. The other thing is that there is something called strongly connected components and weakly connected components, right? Strongly connected components is that if you have some vertices which are connected over here, so all of these are reachable from each other. And then you have some vertices which are connected over here, right? These are also all reachable from each other. But then this set B is reachable from set A, but set A is not reachable from set B, right? So you get two kinds of connected components, strongly connected components and weakly connected components, right? A and B are strongly connected components, but together they form a weakly connected component, right? If you ignore the directions, right, then it becomes a weakly connected component. So this algorithm, does it work for strongly connected components or weakly connected components?
Weakly connected component. Yeah.
Weakly connected components.
I mean, if we have strongly connected component, then we are obviously talking about directed graphs.
So that's the whole point. Does this algorithm work for directed graphs? That's the question, right? Can I make it work for directed graphs?
We can, I mean, so we can just apply it. I mean, we have this DFS and we can use it as a black box in a strongly connected connected components algorithm, right? Where we construct that metagraph.
So this union find data structure will not work, right? You'll have to use something different. The union find, it just has the notion of sets and it keeps on doing a union of the set. There's no notion of direction or anything over here, right? It's working in set notation. So there we are losing the directionality component, right? So how do you do strongly connected components? Well, maybe you can modify this algorithm. I don't know. Think about it. But what else can you do? So we can basically use this algorithm we did last class, right? This was the transitive closure. What is transitive closure? Transitive closure tells you all the vertices that can be reached from each vertex. Yeah, remember? So if you look at a row in the adjacency matrix, if there's a 1 at an entry, true at an entry, it means that that vertex is reachable from you in the directed graph, right? So again, you need a little bit of work more to go from a transitive closure to strongly connected components. Okay, what is that work? From the transitive closure, right? One problem with transitive closure is so it's not symmetric, right? The adjacency matrix is not symmetric. So if there's an entry ij, right? And there's a entry ji, right? If it's not symmetric, it's possible that this is true and this is false, right? ij is true and ji is false. If there's a path from I to j, but there is no path from j to I, right? So now what I can do is I can distribute this amongst all the processors and I can examine this. For every entry ij, I just check ji. If these two don't match, then I make both of them false, right? So I'm kind of like disconnecting my graph. So after this, there won't be any edges which are unidirectional. You won't find any edge that I can reach j, but j cannot reach I because I've made all those edges false. Okay. Not edges, I shouldn't call these edges. These are paths, right? In the transitive closure. If there's a connected component like this and there's an edge going like this, essentially what we've done is we've removed this edge, right? So now your adjacency matrix represents a set of cliques, right? There'll be a clique for every connected component. And then you can just pick up the cliques. Okay.